Hey guys, welcome back to another lecture video for Chem 115. Now, for the past two lecture videos, we've been talking about chemical systems that has achieved a state of equilibrium, which can be quantified or represented by the equilibrium constant Kc. But what do we use to represent chemical systems that is not at equilibrium? For instance, what if the chemical reaction has just started? Or perhaps the chemical reaction did achieve a state of equilibrium, but somehow it was disturbed. Now, it turns out that we can represent these types of states through the use of the reaction quotient, which is given the symbol capital Q. And so the remainder of this lecture video discusses what the reaction quotient is and how we can use the reaction quotient Q and the equilibrium constant Kc to better understand how the reaction will progress, whether it'll move towards the forward or reverse direction, so that the chemical system can achieve a state of equilibrium. So let's go ahead and get started. And so the reaction quotient Q, it's a value that represents the quotient or the ratio of the activities of the product to the activities of the reactant at any time period during the course of the chemical reaction. And so what do I mean by activities? So we can think of activities as the rate of the production of products, meaning the rate in the forward direction, or the rate of production of reactants, meaning the rate of the reverse reaction. And so if we take the ratio of the activities of products and reactants, then that's going to represent the reaction quotient Q. And so it turns out that the actual value, the quantity that would represent Q, is not constant like the equilibrium constant. And so the reaction quotient Q, its value changes as the reaction system approaches equilibrium. And so for us to better understand both these points, I want to go ahead and draw your attention to this graph that's found in the bottom left corner of the screen. And so first of all, we're going to go ahead and use this brown dot as our reference point as to where equilibrium will start. And so everything to the right of that brown dot is going to represent the chemical system being in a state of equilibrium. And anything to the left of that brown dot, which is basically this whole entire thing, is representing a state that's not at equilibrium. And so looking at the y-axis, it's representing the rate of the reaction. The x-axis is representing time. And so if you guys look at the state in which the chemical system is at equilibrium, notice that the rate of the forward and the rate of the reverse reaction kind of flat lines. And so in other words, when you calculate the equilibrium constant Kc, this value does not change once the chemical system has achieved a state of equilibrium. And so if we look at the region in which the chemical system is not at equilibrium, the rates kind of change as the reaction progresses between the forward and the reverse reaction. And so the reaction quotient Q is a quotient between the two rates of the forward and reverse. And to better understand why the quantity of Q changes as the reaction progresses, we can go ahead and pick three different snapshots in time, which is going to be represented by T1, T2, and T3. And so if we wanted to understand the value of Q at this specific time period, then we would go ahead and take the rate of the forward reaction and the rate of the reverse reaction and set them as a ratio to each other. And if we do that, what we get is the reaction quotient at the first time period, which is going to be represented by T1. And so I want you guys to notice that as we progress in from T1 to T2, the slopes changes compared to T1. So therefore, the rate of the forward reaction and the rate of the reverse, when we take the ratio of them, that value is going to change. And so therefore at T2, at time period 2, the reaction quotient Q, or I'm going to say Q2, so Q2 will represent the reaction quotient at time 2. The value is not going to be the same as Q1, the reaction quotient at time 1. And so if we apply this logic to T3 or time 3, once again notice that the slope of those two lines, it's different than the slope of these two lines and the slope of these two lines. And so therefore, if we take a ratio of those two activities, the value for Q3, so which is the reaction quotient at time 3, is once again going to be different than Q1 and Q2. And so another really interesting point about the reaction quotient is that the reaction quotient Q does not equal to the equilibrium constant. And when it does, then that means that the equilibrium, or that means that the chemical system is at a state of equilibrium. And so there is only one condition where the value of Q does equal to K. In other words, the reaction quotient is equal to the equilibrium constant. And that's when the reaction is at an equilibrium. And so that can be represented by T4. So time 4, if you look at its position on the graph, this dot on the line is in the region of which the chemical system is at a state of equilibrium. And so we know that T4 is going to be represented by the equilibrium constant Kc, but we can also, but it is, at that point where the value of Kc is equal to Q as well. Okay. So we don't really utilize Q when the chemical system is already at the equilibrium or at an equilibrium. And so I just wanted to point out that the reaction quotient Q, the value of it does equal to Kc when the system is at equilibrium. But, if the system is at equilibrium, then there's really no point. Oops. Oh well, whatever. Let's just leave that in. There's really no point for us to represent Q. So I'll just scratch that out. All right. And so we can go ahead and write the mass action expression for Q in a very similar way that we wrote the mass action expression for Kc, in which the mass action expression for Q represents the ratio of the concentration of the products raised to their coefficient. I'm just going to represent coefficient as X just in general, over the concentration of the reactants raised to, once again, their own coefficient. And so if we wanted to calculate the reaction quotient, we can go ahead and write the mass action expression in a similar way that we did for the equilibrium constant, where the equilibrium constant Kc is represented by the concentration of substance C raised to its coefficient, substance D raised to its own coefficient, over substance A raised to its own coefficient, times that by substance B raised to its own coefficient. The only difference is that the concentration of C, D, A, and B represents the equilibrium concentration of those substances, where the concentration of these substances is not at equilibrium. Okay. And so that's really the difference between the mass action expression for the reaction quotient and the mass action expression for the equilibrium constant. Just the concentrations for the mass for the reaction quotient does not represent the equilibrium concentration. It could if Q equals to Kc, but it might not. So we're just going to leave that blank. In other words, we're not going to write this subscript EQ for the concentration. All right, so now that we have a better understanding of the reaction quotient Q, we're going to go ahead and learn how to compare Q, the reaction quotient Q, and Kc. And so it's great that we have some way to quantify Q and we have some way to quantify Kc, but if we start comparing these two values, what information does it hold for us? What information can it tell us? And so the only thing that we know so far, based on the previous slide, is that when the reaction quotient Q, the value is equal to the equilibrium constant K or Kc, that's telling us that the reaction is at equilibrium. Okay, so that's the only piece of information that we know when we compare Q and K. But that's not the only condition. What if Q is greater than K, or what if Q is less than K? What information do those two scenarios tell us about the reaction system? Now, for us to better understand those two scenarios, we have to understand, once again, what the reaction quotient Q and the equilibrium constant K represents. And so it turns out that, let me just go ahead and write it up here. It turns out that the meaning behind Q and K, they're very similar, but they're just different in the sense that one's at equilibrium, the other one is not. And so if you recall, the equilibrium constant Kc is a ratio of two rate constants, the rate of the forward and the rate of the reverse. And so the reaction quotient Q is actually the same ratio, right? It's a ratio of the two activities of the forward and reverse. But the only difference between the two is that the rate constants at when the system is at equilibrium, these two rate constants, for lack of a better word, converge to represent the system at equilibrium. So remember the definition of the equilibrium, that's when the rate of the forward is equal to the rate of the reverse. Okay, so in a sense, the rate has converged, right? So this is where equilibrium occurs. And so the ratio for the reaction quotient between the two rate constants, the forward and reverse, does not represent the rate constant, the rates at equilibrium. Okay. So it hasn't yet converged, if you will. And so these instantaneous slopes that I've drawn here on this graph represents the instantaneous rates at specific time periods. And notice how they haven't converged just yet. They're still kind of separate. And so we're going to go ahead and take this definition of K and Q to help us understand the relationship between Q and K. And so we're going to go ahead and look at the first scenario in which the reaction quotient is less than K. And so if we were to somehow calculate Q and calculate K and compare these two values, and if Q is less than K, then what information is that telling us? Well, based on this paragraph that you guys see here, it's telling us that the reaction vessel has too many reactants. And for the system to move towards equilibrium, reactants must be converted to products. And so for the only way for reactants to be converted to products is to move in the forward direction. And so it is moving in the forward direction that will allow that specific chemical system to achieve a state of equilibrium. So I just want to highlight a few points here. And so first and foremost, when Q is less than K, reactants must be converted to product so that the reaction can move toward equilibrium. And so overall, the reaction will proceed in the forward direction to attain that state of equilibrium. Now let's go ahead and look at the second scenario. And so when the reaction quotient is much greater than the equilibrium constant, it's telling us that the reaction vessel currently has way too many products. And so for the reaction system to achieve a state of equilibrium, products must be converted into reactant. And so the only way that that's possible is if the reverse reaction occurs or proceeds so that the reaction system, or so that the chemical system can reach a state of chemical equilibrium. So once again, when Q is greater than K, it's telling us that we have way too many products and we must convert products to reactants. And the only way for us to do that is for the reaction to proceed in the reverse direction to reach equilibrium. Okay. And so it's great that we have all of these facts that describes, this scenario, but what we want to understand is why, right? Why must, when Q is less than K, why must reactants be converted to products? Or products be converted to reactants when Q is greater than K? And so we're going to go ahead and explore, we're going to answer those two questions in the next slide. And so, just focusing on this first scenario, I'm not really discussing it too much just because it is what it is. So when Q is equal to K, the reaction is at equilibrium. Done. And so when Q is less than K, remember that the reactants must be converted to products so that you can reach a state of equilibrium. And for us to understand why this must be the case, we're going to go ahead and visit the definition of the reaction quotient and that of the equilibrium constant. So if you guys recall, the reaction quotient is a ratio of the two activities in the forward and reverse. Same idea with the equilibrium constant. Now, to better make sense of this, we're going to go ahead and plug in just random numbers that would make this specific statement true. And so for Q to be less than K, we have to have a value for K that's greater than Q. And so what I'm going to choose two easy numbers. It's going to be 10 and 1. So 10 is greater than 1. That's a true statement. And so these values will represent just like a relative rate. It doesn't have to be 10 and 1. It can be any two numbers that you want it to be. It just needs, the statement must be made true. So Q must be less than K. So it can be like 1 here and a million there or something like that. It doesn't really matter. And so we're going to go ahead and visualize, for the sake of this argument, that these numbers will represent the relative rate. And so if Q is equal to 1, or 1 over 1 to be more precise, so that it represents the K of the forward, the rate constant of the forward and the rate of the constant of the reverse. We can do the same thing for K. The rate, sorry, not the rate constant, the equilibrium constant K, 10 over 1. Oops. And this 10 over 1 is going to represent, the K of the forward and the rate constant of the reverse. Okay. And so what we did is we chose two numbers, 10 and 1, and we turned it into a fraction so that the fraction kind of overlaps the relative rate of the forward reaction and the relative rate of the reverse. So same thing here. Okay. And so once again, we're going to represent, 10 and 1, these numbers, as the relative rates of the reaction. And so looking at what we have right now, our goal is to make Q equal to K. Okay? And so if you look at the number, right, so of the rate of the forward, so real quick, once again, this 1 represents the relative rate of the forward, and this 10 represents the relative rate of the forward reaction at equilibrium. And so notice that they are not the same. 1 and 10 is not the same. And so for us to make Q equal to K, the rate of the forward in the course of this chemical reaction must increase until it reaches this value, if you will, which is going to represent the equilibrium. Okay, and so for Q to become K, the forward reaction must dominate. Okay, and it is when the forward reaction that occurs that allows Q to become K. Okay, so 1 must turn into 10 if you think about it that way. Okay. And so overall, this is the reason why to reach equilibrium, reactants must go to products, right? And the only way for reactants to go to products is for the forward reaction to occur, or for it to dominate during this time period so that equilibrium can be reached. And so let's go ahead and look at the second scenario in which the reaction quotient Q is greater than the equilibrium constant K. And so according to what we've learned, for the chemical reaction to reach a state of equilibrium, products must be converted into reactants. And why is this so? Once again, we're going to go ahead and use the concept, the definition for Q and K to better understand why products must be converted to reactants to reach equilibrium. And once again, we're going to go ahead and pick two numbers that will allow us to make this statement to be true. And you guys can use any two numbers, but I'm just going to be consistent. I'm going to choose 10 and 1. And once again, 10 and 1 are representing the relative rates for the sake of this example. And so if the value of Q is equal to 10, or 10 over 1, the reason why I'm putting everything over by 1 is because if you take 10 divided by 1, it's still 10, so we don't really change the actual value. We can go ahead and overlap this fraction with the rate constant of the forward and the rate constant of the reverse. Okay. For K, if you recall, we gave a relative value of 1, and we can write that as a fraction by putting 1 over 1. And once again, we can overlap the numerator with the rate constant of the forward and the rate constant of the reverse. And so this 10 represents the relative rate of the forward. This 1 represents the relative rate of the reverse for Q. This 1 represents the relative rate of the forward. And this 1 represents the relative rate of the reverse for the equilibrium constant Kc. Okay. All right. And so once again, the goal, very similar to the previous example, is to make Q into K, the equilibrium constant. We want to make the reaction quotient, we want to have the reaction quotient equal to the equilibrium constant so that the chemical system can reach a state of equilibrium. Okay, that's the goal. And so if you look at the numbers, here we have 10 and 1. And so how can we make 10 over 1 equal to 1 over 1? Okay. And so to make 10 over 1 equal to 1 over 1, we must increase the value in the denominator for Q. Okay, so in other words, one way to make 10 over 1 to equal to 1 over 1 is to make 10 over 10. Okay, because 10 over 10 is equal to 1 over 1. And so what this is telling us is that the reverse reaction must dominate so that the reaction can reach a state of equilibrium. So thus, the reverse reaction must dominate for the system to reach a state of chemical equilibrium. Okay, so we're going to increase this value so that Q becomes K. And so since the reverse reaction must dominate, that's telling us the products must turn into reactants for the equilibrium to be reached. Whereas in the previous example, or previous scenario, when Q is less than K, the forward reaction must dominate. So therefore the reactants must go to products. Okay, I highlighted that last bit just for just so it's consistent. Okay. All right, so we can go ahead and visualize this by looking at this image. Now, real quick, if you guys didn't really understand this train of thought or logic, that's okay. This is just like a proof. It's just a brain exercise, if you will. The really important thing is to understand the direction. If when Q is less than K, reactants must go to products, so it's proceeding in the forward direction. When Q is greater than K, the product must be converted to reactant so that the reverse direction must occur. And so one trick to memorize the relationship between Q and K is to think of the inequality as the mouth of the Pac-Man. Also, for this trick to work, Q must always be written first. And so what do I mean by this? Okay. And so if we kind of draw, a Pac-Man out of this inequality. Remember, I don't know if you guys have played Pac-Man, but feel free to watch a video if you want. But basically, the direction that the Pac-Man will move is in the same direction that the mouth points. So if the mouth is pointing in this direction, then that's basically where the reaction will progress. Okay? And so if Q is less than K, then the reactants will be converted into products. So therefore the forward reaction will occur, will dominate so that the reaction can move towards a state of equilibrium. And I want you guys to notice that I'm always writing Q first, right? If you guys write K first, your inequality might not be consistent with what's actually happening. So it's kind of tricky. And so if I do the same thing for this second example, for this second scenario, in which Q is greater than K, notice that the opening of the mouth of the Pac-Man points towards the left. And so therefore, for the chemical system to move towards equilibrium, the reverse reaction will occur, meaning that products will be converted into reactants. Okay, and once again, Q is always written first. All right, and so hopefully that gives you a better idea of the reaction quotient Q. Remember that the reaction quotient Q just represents the relative activities. It's a quotient of activities of products to reactants, really at any stage during a chemical reaction. And so it can be before equilibrium is reached, or when equilibrium is reached, or perhaps, if equilibrium has reached and there was a disturbance in the equilibrium, Q can also represent that as well. All right, so that's pretty much it for this lecture video. We're going to go ahead and move on to another concept in the next lecture video. Bye.